All right, we've seen how if you have an electric current that is moving charges, it creates a magnetic field according to the right-hand rule, giving you circular lines of magnetic field surrounding the wire, which we'll use in just a minute. But it turns out, as they discovered in the early 1800s, it was Michael Faraday in 1831, in fact, that a changing magnetic field can also induce a current, an electric current, in a wire. We call this magnetic induction. And this graphic here, this animated graphic, shows us that we have, let's say, a bar magnet inside a loop of wire, and if that bar magnet leaves, a current is induced in the wire. Well, that's maybe not so convincing because it's just a computer animation, but we can do it in real life here using this actual loop of wire. This is a copper wire loop, many turns here, connected to a simple voltmeter. Now we can do exactly the same thing as is in the animation up there, put a magnet inside here and then pull it out. And if you look carefully at the tip of the arrow on the voltmeter, you see that it moves. When the magnet goes in, you get a pulse. You get a pulse the other direction when it goes out. Well, that's not terribly impressive, so we have a much more, much stronger magnet here. And if I take this loop and I pass it in between the poles of the magnet, you'll see what happens. Again, watch the tip of the arrow on the voltmeter, and you see you get a pulse of voltage in one direction when I go in, and then when I pull it out, you get a pulse of voltage in the other direction. And indeed, there's current flowing one way and then the other way, depending on whether the flux is going in one direction or the other. Now, I use that word flux. What does that mean? Well, there are a couple ways to think about how this current is induced. We already saw that if you have a charged particle and it's moving in a magnetic field, it feels a force. Okay? Well, imagine an electron in that loop of wire. As it's going past the magnetic field lines here, it feels a force in a certain direction. And if you work out for every electron in the loop, the force that it feels, there's a net current in one direction or the other, depending on which way the charge is moving. So that's one way to think about it, just in terms of the magnetic force we already know about. But we can also describe it in terms of magnetic flux. And how does that work? Lenz's law, which came just a few years after Faraday's discovery of this effect, says that the current that's induced in a loop of wire flows in a direction which tends to oppose the change in magnetic flux through the loop. So first we have to understand what is magnetic flux. If you have a magnetic field, which we call B, and suppose there's magnetic field lines all over this loop, if we take the magnetic field, multiply it by the area, that gives us the magnetic field, magnetic flux. You should think of the magnetic flux as basically the total number of magnetic field lines times the area here. Or you could think of it as just the number of field lines if you want. Now this is a vector quantity. It's pointing to the right here because we have this magnet going, the magnetic field line inside the magnet is going from south to north, and remember they curve around and then they go back in the south end. As the magnet leaves the loop, then this magnetic flux goes from pointing in the right-hand direction to, well, a smaller vector still pointing to right. I say on the slide it goes from right to left, but it doesn't quite go all the way to the left because you still have a weak magnetic field going into, from out here into the south pole of the magnet. But if you have the magnetic flux changing from positive to negative, you will get an induced current in the loop. We can figure out that direction from Lenz's law by considering what is the change in flux and what current would you need to oppose that change. So let's use our right-hand rule to do that. In this diagram, the loop is such that it's going into the screen here. So suppose we have a current which is going up. What magnetic field would that produce? Well, we use our right-hand rule where we grasp the wire, thumb going in the direction of the current, and then our fingers wrap in the direction of the magnetic field lines. And indeed, you see that your fingertips are then pointing in that direction, out of, or to the right in this drawing. And so by having a current creating such a magnetic field, that tends to oppose the change that we made by removing the magnet. Okay? So again, magnetic flux is just the magnetic field times the area. If you have a uniform magnetic field like the one shown here pointing to the right, all the arrows point along the magnetic field lines to the right, and the magnetic field is the same everywhere on the loop, then if the loop is oriented perpendicularly to the field, the flux is just given by B, the magnetic field strength, times the area. Now imagine we take the loop and we turn it flat so that none of the magnetic field lines are going through it. In that case, even though you're still in a region where there's a magnetic field, a uniform magnetic field, none of the field lines go through the loop, and hence the magnetic flux is equal to 0. So just by taking this loop and turning it sideways, we've gone from having some flux to having 0 flux. And the current that's induced in the loop is proportional to the time rate of change of the magnetic flux through the loop. Now this is the physics on which a very common and very useful device is built, the electric generator. If you have any source of mechanical energy which can turn a crank, whether it's your hand turning the crank, a wind turbine, water, even steam turbine from where the steam is heated from a nuclear power plant, anything that gives you mechanical force turning a shaft can turn a loop of wire, and if you turn it in a big magnetic field created by permanent magnets, then you will get an electric current induced in that loop. And that's sort of indicated schematically here with this big C-shaped magnet here, and you turn the crank and this loop turns. As you turn the loop, the flux through that loop is oscillating up and down sinusoidally, and hence the current that's induced goes through the light bulb here is a sinusoidal current. That's what we call alternating current, and that's one of the reasons that we have alternating current as the dominant electrical power source all over the world, is that it's based on generators whose shaft is rotating 60 times a second or 50 times a second, depending on where you are in the world.